Good morning. I'm Christine Suh. Welcome to this news briefing from the 250th National Meeting and Exposition of the American Chemical Society in Boston. We're joined today by Dr. Challa Vijay Kumar, who's with the University of Connecticut. He'll be talking to us about his new material that could dramatically boost solar panel efficiency. Dr. Kumar.
Thank you, Christine, for the introduction. It's a fun and pleasure to present our work at this conference. And in the first slide, we show that with the help of one of my colleagues, Dr. Jay He, and my graduate student we share with, we created new and novel materials that are biodegradable. And also at the same time, these function as coatings for solar cells and also for light-emitting diodes. So if I show the first top reaction, we simply take an edible protein and then mix it up with an edible fatty acid from coconut, and then warm it up and form a gel that contains 95% or so molecular. And what Jingwen did is to mix this gel with dye molecules, 4 different dye molecules. And these absorb in the blue region and the green and yellow regions of the solar spectrum, but then emit in the red region. And this way, these coatings convert the blue and other colors into the red. It so happens that a large number of solar cells are less sensitive in the blue region and more efficient in the red region. So by coating this, as shown here, in a cell such as a Gretzel cell, we can boost the amount of red light the cell receives. And therefore, we can boost the power output of this. In the next slide, what Jingwen did was very clever. She omitted the 4th dye molecule and uses only 3 dye molecules, the same protocol, and then it absorbs the blue light or near UV and then emits pure white. And these are wonderful for coating light-emitting diodes that mostly emit in the blue region. They can be converted into nice ambient white light. And the important part is that these materials that we're making, biodegradable, bioabsorbable, biocompatible, bio this and bio that. So instead of saying all that, we call them as edible. So it's a new way of thinking about biologically relevant and interesting materials, but at the same time, they should be functional. So that's the crux of this discovery.
Great, thank you. Do we have any questions? Yes, Kath.
So it's Kath O'Driscoll from Chemistry and Industry magazine. Just to ask, first of all, by how much can you boost the output of the solar cells using these new coatings? Excellent
question. It depends on the efficiency of the solar cell that you start with. For example, silicon single crystal cells are on the high end of the efficiency spectrum. And the cell like the Gretzel cell that we showed has on the low end of the spectrum. So those cells that have low efficiencies, for example, Gretzel cell, which is very inexpensive, and we can boost the power by a large amount. Those on the other end of the spectrum, we may not be able to do so as much as we can do with the other ones. So there are specific cell types that can benefit a lot from this sort of coatings.
Percentage of, even very roughly, or a range of sort of by how much you expect to be able to boost?
Oh, that's an excellent question. It's very difficult to predict how much you could. What I can tell you is what we found. In this particular coating, we are able to boost at least twice. This is very, very preliminary work. We're just learning to build these cells, right? So we're just beginning, and we already see it twice as much or so.
Gretzel cell, is it?
Yes,
you're using?
with the Gretzel cell.
But are most commercial cells, are they silicon-based?
Yes. Most popular cells that you see on the rooftops are silicon cells. And we are now collaborating with a company in Connecticut to apply these coatings on these traditional solar cells, silicon-based cells, look for improvements in the power. And what they tell me is, even if the efficiency of these silicon cells can be increased by, say, 0.5%, it is still very exciting for them. So that's very encouraging. I didn't expect that. I thought it would want some 10 times or 5 times more increase, but of course not possible.
I'm just about to have solar cells. I'm just about to have solar cells fitted. I mean, could this be retrofitted? Could you apply the coating?
The retrofitting could be quite hard. What we're trying to do is to integrate these coatings into the manufacturing of the cell itself, so that the new cells will have these features associated with them. But it's a long way to go. We still learn a lot about these cells.
Thank you.
Yes.
Kiki Sanford, This Week in Science. I'm wondering, how perfect is the energy transfer from the blue to the red light? What percentage of the energy that comes in is then sent on to be absorbed by the solar cells?
Oh, excellent question. Excellent question. We call this as blue to red conversion efficiencies. And as I can see here, I will have a prop that I will demonstrate. And I have, let's say, a blue emitting diode here on this side, and then a white emitting diode on the other side. So when you can turn it on, you can see that very, very little faint blue light you can see. But on the other hand, the LED that is coated with our white phosphor, you see bright white in color. So that itself tells you, there is a lot going on in here and converts the blue to the white. And in the same way, the blue is converted to the red light in the case of these coatings. Now, to be very technical, we expect around 2 to 3 times increase in the number of photons that you can access in the red region because of these coatings, 2 to 3 times. And that depends a lot about what dye molecules we're using and how they are packed in this hydrogel. And so there's a long way to go in understanding what happens and how we can control this. So at least now we're getting 2 to 3 times, so it's a good start.
It is. And I have one last question. You call them biodegradable, so how long would you expect them to last within the integrated manufacturing process you're envisioning?
Yeah, wonderful question. It's a double-edged sword because you want your coatings to last a certain length of time because the end user want to have it, and at the same time, when it is discarded in the environment, you want it to get degraded quickly. So what we have to do then is to define specific conditions under which these things are stable, and define specific conditions under which they can biodegrade. And these are, as you can see, the video going on in here is very, very simple. Take a protein that is edible, and this protein is a waste product from meat industry. People are right now consuming those. And you also take a fatty acid that is actually from coconut, which we are consuming as well. I just learned in the previous meeting, press conference, that the fatty acids we're using are actually insect repellents as well. And so it's an interesting coincidence that also happens to be. And so these are materials that we normally digest and ingest in a normal course of our activities. So there's not a whole lot of chemistry happening here. They're all physically attached to each other, so they can be pulled apart in a much simpler manner in dilution or just throwing out in the environment. And just to make sure that if these are not edible to humans, they're actually edible to microbes and animals or plants. It is edible to someone. So it is a good thing to have.
Okay, so we have an online question from Umair Irfan, who's a reporter with Climate Wire E&E Publishing. The question is, how would this affect the cost of the cell, and how easy would it be to fabricate at scale?
Wonderful question, and complements the questions that are being asked here. And so to give an idea about the cost, we start with very, very inexpensive ingredients. For example, the protein we use here is about 50 cents per gram. As I said before, it's a waste product from the meat industry. And we got tons of this stuff around. And the fatty acids that we're using here is byproduct from coconut oil. And so byproduct coconut oil. So it's also an inexpensive ingredient. And as you can see in the video running there, that it's very easy to make this stuff. You don't need very high-tech equipment to do this. And you can do this in kitchen in your kitchen if you wanted to, right? Very, very simple to make. So that lowers the cost of the manufacture. And also, gives us a modular way. You can put different dye molecules into it and tune the spectrum. Where we want to absorb, where we want to emit, and we want to put more dye molecules to harvest longer wavelengths, or you want to have an LED that is in a bright red or bright blue or bright green. So you have a long list of things you can actually do in a modular way and a simpler way. So there's no covalent chemistry associated with it. So it's a physical process, and that's really, really good.
Do we have any other questions? I know that the work is very preliminary, as you mentioned,
Yes.
but do you have any best guesses as to how long this might take to become incorporated in a manufacturing process?
Oh, that's a great question. And a lot of that depends on, you guys out there and the National Science Foundation. It depends on the commercial interest. And, there's never enough funding to do these kind of activities. So if an industrial partner steps up and comes to us and gives us the necessary funding, this can be accelerated quite quickly. And as I was alluding, there's a company in Connecticut that is already testing, these coatings for solar cells, silicon solar cells particularly. But we're hoping that there will be other commercial interests that will come through for particularly the grid-cell cells, because they're quite cheap. And right now, the problem with them is the efficiency of those things. So if you can boost the efficiency of those cells, then they become competitive with silicon cells. And so it'll have a lot more impact on solar energy harvesting.
Great, thank you. Any other questions? I think that's it then. All right, thank you very much, Dr. Kumar. It was very interesting. The archived version of this session will be posted at bit.ly/ACS Live Boston. Please join us for our next press conference today at 1 p.m. on a paper-based test for Ebola. Thank you.
Thanks, Christine.